Hey class, we're going to move on to a new unit on similarity. We got a few things that we're going to cover in the entire unit. Ratio and proportion, similar polygons, triangles that are similar, similarity in right triangles, which is fun, and proportions in right triangles. But we're going to start with ratios and proportions, and we're going to attempt to chunk this. I'm going to make a few different lessons from just this one, because there's a lot to cover, and this is really, I think anyway, really important stuff. So the only thing we're going to talk about in this particular video are just these two elements, setting up ratios and scale factors. Then we'll just build on it because I want to try and cut down the amount of time per video. So we're going to talk a lot about ratios right now, and that's what we're going to focus on, is just ratios. And why? Because it's so darn important. So let's start with some notes, and we're going to spend a lot of time talking about this. We have to understand that what a ratio is. A ratio is just the comparison of any two values, and it could be any two values. We can compare anything. Okay, so that is what a ratio is. Now, there are a few famous ratios you might not even know about, but they are still ratios. One example is something as simple as speed. Okay, so what we think of in terms of speed is actually a ratio. When we talk about speed, we talk about miles per hour or kilometers per hour for anyone that's working in the metric system out there. And so we call it MPH. Now we see that, we take it for granted, but that is a ratio. We are comparing two values. We're comparing the amount of miles to the amount of hours. Okay, and in the case of miles per hour, we're talking about how many miles in 1 hour, but still, that is a ratio. That's what a ratio is. Another example, and we've covered this a bunch, is slope. Slope is also a ratio. It's a rate of change in the dependent variable to the independent variable. And so we look at our slope formula that we're so used to seeing. Well, that's a ratio. We're talking about the ratio comparing rise to run, the change in the y over the change in the x. Okay, so that also is a ratio. We talk about slope. And here's another one we might not think about, but pressure. We talk about measuring pressure. It's a thing that can be measured. We measure it in what's called PSI, which means pounds per square inch, which is pounds per square inch. But what are we comparing? It's a ratio. We're comparing weight to area, right? So you might be thinking, wait, Mr. Katz, we can compare weight to area? Yes, we can. When we compare weight to area, that's pressure. You know, how much pressure am I putting on a thing? That is measured in PSI. That is also a ratio. So we've got to know what ratios are. Okay, so that's a helpful thing. But now there's another thing that ratios are. We don't think about it too much. We can think, again, in ratio comparing two qualities, we can think about ratios as conversions. Okay, so when we talk about converting things, those are ratios. Because when we convert one thing to another, we are comparing two different values. Okay, so a conversion is also a ratio, and here's an example. We know about a minute, right? We talk about time, tick-tock, tick-tock. 1 minute is 60 seconds. That's a ratio. It's 1 minute to 60 seconds. We're going to use this a little bit later. And we talk about inches to feet. Okay, so we have, well, 12 inches is 1 foot. As a ratio, 12 inches is 1 foot. Okay, we can talk about miles, right? 1 mile is 5,280 feet. So as a ratio, 1 mile is 5,280 feet. And so we talk about conversions, we can talk about ratios. Now, here's the important note. We start getting into ratios, and we will. Okay, it's important to label your ratio so you know what you are comparing. So example we just did, we labeled miles and feet. We labeled inches and feet. We labeled minutes and seconds. Whatever we're doing, we label, so we know what it is we are comparing. Okay? Okay, so let's do an example, right? I drew a neat, found a neat picture online. Hey, it's a Corvette. Woo! Try and get the boys engaged. Anyhow, so we have this example. Okay, the Corvette C7 Stingray Coupe, the actual car is 176.9 inches long. I Googled it. Okay, so the actual car is that long. Now, a model car of the same make has a scale of 1 to 18. That's how we read this. We read this 1 to 18. That's how we read that. So it's a scale, okay? And how long is the model? Now, we're not going to solve this equation, but I want you to see how we can use ratios to set this up. What are we talking about in this example, besides the awesome Corvette Stingray? We're talking about a ratio. Okay, we're going to figure out the size or the length of the car as compared to the size or the length of the model. Now, what does this scale tell us? The scale of 1 to 18. What the scale means is that one car is made up of 18 model cars. Okay, so that's what it means. One car is made up of 18 model cars. So when we compare a car to the model, that's what scale actually means. We'll talk more about that in a second. So when we see this particular example, when we set up a ratio, this is what the ratio would look like. Okay, so we have 1 to 18. So what is that? It's 176.9 to however long the model is, and that's the question. Again, we're not going to solve it right now. We're just making sure that we are labeling our ratios and understanding what ratios are. Okay? So now let's get into another example. Right? It's the same type of thing. Yay, Corvette. So this example now here is the same question, right? The Corvette C7 Stingray Coupe is 176.9 inches long, right? We've established that. Thank you, Google. Now, a model car of the same make is 4.114 inches long, right? So it's a tiny little model car. What is the model's scale? Okay, so now here's the actual question. What is the scale? Now, the ratio of the actual car size to the model car size is the scale. So we have to make sure that we understand that vocabulary. So how is this going to work? How are we going to think about this? We're going to set up a ratio. So what is the ratio? What are the two values we are comparing? We are comparing the car to the model, right? The actual physical car to just the model itself. So this example, the car, the actual car is 176.9 inches, and the model itself is 4.114 inches. So that's the setup, right? That's the ratio. So how do we find the scale? Well, remember how the scale works. The one car is how many models. So how does this work? We're simply going to divide to find the ratio. So when we divide these two numbers, we're going to get close to 43. Okay, so when we divide these two numbers, we get 43. So what does that mean? But what does that mean, right? So what does this mean if we get 43? So what? So what this means is that it takes 43 model cars to make one actual car. That's what this means. Okay, so it takes 43 model cars to make one actual car, and the way we write that is 1 to 43. So one actual car is 43 model cars long. That's the scale. And that's how we work with that. Now, here's another way of saying this because we get into more vocabulary. Another way of saying this is that 43 is the scale factor. Okay, 43 is the scale factor. So however long the model car is, if it has a scale of 43, we multiply that distance by 43. That's the scale factor, and we'll get the actual size. Okay, so that's what the scale factor means. All right, a couple more examples, and then we're done because I'm already talking too long, but I want to make sure we understand this stuff. Okay. So here's an example. We're going to write a ratio. So here's an example. Bonsai trees. Well, the bonsai bald cypress tree shown here is a small version of a full-size tree. Now, in Longwood, Florida, a bald cypress tree called the Senator, we have a tree around here we're used to anyway, called the Senator. It stands 118 feet tall. Okay, so we know what's going on. The actual tree is 118 feet tall. What's the ratio of the height of the bonsai, this little guy? What's the ratio of the height of the bonsai to the height of the Senator? So how are we going to do this? Right? We are comparing two values, so it's extremely important to set up the ratio. Now, in this case, words matter. So when we talk about the ratio of the height of the bonsai to the height of the Senator, the actual tree, we have to be careful with words. So we're setting up the ratio of the bonsai to the Senator. Those are the two things that we are comparing. Words matter. So if we were comparing the Senator to the bonsai, it would be the other way around. Notice how we're comparing the bonsai to the Senator. Words matter to set it up this way. Okay? All right, so make sure you understand that. Now, units also matter. And so what we're going to do is play a game called dimensional analysis because units matter. Now, we can't just willy-nilly throw numbers around because we have numbers, right? 118 feet here and then 15 inches here. we can't just throw those numbers around. Units matter. So when we talk about the height of the bonsai, we know that the height of the bonsai tree is 15 inches. Okay, units matter, and so we're going to label our units. It's 15 inches. And we're going to compare that to the senator. It's 118 feet. Units matter. So we have our setup. This is our ratio. It's 15 inches to 18 feet. Now we're going to play a game called dimensional analysis, and that is used to convert. Okay, so when we talk about dimensional analysis, we use this to convert units of measure. So what are the units of measure we're looking to convert here? We have inches and feet that we're playing around with, and we want to make sure that we're using in the same measurement, right? So in the same units of measure. So what is it that we know about inches and feet? If we remember from the notes, or I don't want to say common sense, but we need to know some basic things about life. For example, it's 1 foot is 12 inches. Okay, so that's an important thing. Remember from the note we had 1 foot is 12 inches. So how can we play with dimensional analysis? We know that 1 foot is 12 inches. So we could say that 1 foot is 12 inches. Now, why would I write it this way? I have to write it this way, but there's a reason. Because when we look to use dimensional analysis, we're going to look to cancel our units to make sure that we are working in the right way. Now, the question is asking about a ratio. What's the ratio of the heights? The bonsai tree. Does the ratio have a unit of measure? No, a ratio is just a scale. It's something to something else. So in this case, the way we have set up our units of measure, the units will cancel. Feet cancel with feet, and inches cancel with inches. So the ratio is what we have left. So what do we have left? Well, what we have left is multiplication. And then, as you remember, when we multiply our fractions, we multiply numerators times numerators and denominators times denominators. So we have 15 in the numerator and 118 times 12, which I totally cheated and used a calculator. We have 1,416. Okay, so when we have our units of measure, we set it up this way. Now, is this simplified? The answer is no. This is not simplified because here's a number trick. I'm going to teach you a number trick. We know that in the numerator, it is divisible by 5, and in the denominator, it is not divisible by 5. But in the numerator, this is divisible by 3. Is the denominator divisible by 3? And the answer is yes. Here's how I know. If I add the digits, I have 1 plus 4 plus 1 plus 6. That equals 12. And 12 is divisible by 3. Okay, so what does that mean? That means the entire number, 1,416, is divisible by 3. So I can divide the numerator and the denominator. So when I simplify everything, I have 5 in the numerator, and in the denominator, 3 goes into 14, let's see, 4 times, with a remainder of 2. 3 goes into 21 7 times, and 3 goes into 6 2 times. So our ratio is 5 to 472. And so that's the answer, right? 5 to 472. That's the ratio of the bonsai tree to the senator. And that's how we write ratios, okay? So here's another example. I'll do this one really quick. Bonsai tree is 18 inches wide and stands 2 feet tall. What's the ratio of the width to the height of the bonsai? So we are comparing width to height. Okay, remember, words matter. So we're looking for the width. It's 18 inches wide. And then we look at the height. It's 2 feet tall. But we need to be working with the same units of measurement, or in this case, with no units of measurement. And so we use dimensional analysis. We know that 1 foot is 12 inches. And then we can cancel our units. Okay, feet canceling with feet, inches canceling with inches. So we will be left with 18 in the numerator, and then 2 times 12, 24 in the denominator, and both of those values are divisible by, you guessed it, 6. Okay, both those values are divisible by 6. 18 divided by 6 is 3. 24 divided by 6 is 4. So the ratio is, of course, 3 to 4 or 3 to 4. And that is how we write ratios. And so I'm only focusing on ratios, and that's it for the lesson. We will come back later and start talking about equal ratios, getting into proportions and all that stuff. But we have to make sure we understand ratios first. Stay tuned, folks. I'll see you later.